Welcome back. Today we're going to talk about a few miscellaneous topics from proof that I haven't talked about yet. First, we're going to talk about a proof method called proof by contradiction. And I'm going to take this opportunity when we talk about proof by contradiction to also review sort of the outline of a direct proof and the outline of a proof by contrapositive so that I can compare and contrast those with the structure of a proof by contradiction. I'm then going to do several examples of what I'll call classic proofs, that is, the proofs that an intro to proof class must cover in order for it to be considered a genuine intro to proof class. So I'm going to prove for you that there's infinitely many primes, and I'm going to prove for you that the square root of 2 is irrational. And then finally, I'm going to talk to you about some weird proofs that don't use any of the methods that we've talked about so far. That is, I'm going to talk about some proofs where you need some really weird ad hoc method to prove something, just to give you sort of a flavor for how weird the tool set behind proofs sometimes is. That's what I'm going to do in this lecture. Here's what I want you to be doing. As you go through the homework, almost every question on the homework in this section does not require anything from this video. Almost every question on the homework is just something you could have done before, but now you have to look at in the context of everything you know about proofs, and you have to figure out which of the things you know about proofs to use. So, for example, previously, we had a section on proof by contrapositive, and then a homework where you had to do a bunch of proof by contrapositives. But now is the time to make sure that if you come across something that someone asks you to prove, that you know it's a proof by contrapositive. The same thing by proof by induction, and so on. This is your chance to prepare and really make sure you've soaked in all of the material, which I know, especially given the pacing of this course, has come at you really, really quickly. So the homework here is, more than anything, a review guide for the test. That said, once you've learned proof by contradiction from this video, you're welcome to use it on the homework or on the exams if you think it helps you. That said, nothing on Monday's exam will require proof by contradiction. Nothing on Monday's exam will specifically require you to fully grok and answer questions about these particular proofs. And certainly I'm not going to put any proof questions on the exam on Monday that require you to do anything weird. Nor are there any on the homework that I would say require you to do anything especially weird in the sense of the examples that I'm going to come up with here. So, that should give you a sense of where I am, where we are, and where I want you to be. And so before I define the outline of proof by contradiction, let's review the structure of direct proof and the structure of proof by contrapositive. Both direct proof and proof by contrapositive involve proving implications. So in direct proof, what did we do? Well, if we want to prove P implies Q, we started by supposing P, did some math, and then got to therefore Q, and then we were done. Because what we'd shown was in the universe where P is true, automatically Q is true. In proof by contrapositive, we're actually proving the contrapositive implication, which is that not Q implies not P. So the outline looks like suppose not Q, then math, therefore not P, and then we're done. Unlike direct proof and proof by contrapositive, proof by contradiction does not require you to be proving an implication. Proof by contradiction can theoretically work for anything you want to prove. What does the proof look like, though? Well, if the thing I'm proving is R, then the proof starts, rather bizarrely, with suppose not R. So again, if I specifically want to prove a particular statement, I start a proof by contradiction by supposing that that thing is false. And you should always say, suppose for sake of contradiction or whatever phrase you want, again, just so that the reader knows what's going on. So, we start with something like, for sake of contradiction, suppose not R. Then, of course, we have to do some math. And then we get, therefore, and I'm just going to call it Z. And what is Z? Z is some statement that is obviously false. And so what does that say logically? That says that in the universe where R isn't true, Z is true, even though Z is obviously false. And so the word people like to use is, this says the world where R is false is absurd, and therefore R must be true. And everyone has their own little symbol that they like to sort of end a contradiction proof with, but the one I usually see is sort of two arrows pointing at each other, indicating that we now live in a world that doesn't make any sense. Now, why is it that I've put proof by contradiction off until last? And why is it that I'm going to tell you you're not going to use it very often? And the reason why is that the contradiction you reach here has to be something you come up with on your own. And that turns out quite often to be very difficult. It's very rare for there to be a proof that a professor could reasonably ask you on an undergrad homework assignment where you have to produce your own magical contradiction out of nowhere. In direct proof and proof by contrapositive, you have a goal that's given to you in the problem. It's either Q or not P. And since those are sort of given to you, you know where you're starting and you know where you're going, and then you just have to fill in the path in the middle. That's not to say that direct proof or proof by contrapositive are easy. They're certainly not. But certainly, at least knowing where you're going is a helpful clue to start. Proofs by contradiction, you start somewhere, and you're in the middle of a dark forest, and you have no idea where the place you're trying to go is. As a result, proofs by contradiction tend quite often to end up being famous, because they end up usually involving some bit of cleverness that's just so cool that we mathematicians can't help but show them to people and hope that they're excited. That's what I'm going to do today. I'm going to show you a couple proofs by contradiction that are famous and cool, and prove some results that are actually pretty difficult. Now, I want to make an aside about proof by contradiction before we go much further. First, it's generally philosophically considered poor form to use proof by contradiction when it isn't necessary. This isn't something you have to worry about overly much, but proofs by contradiction tend to fall into that same bucket as proofs by induction, where often they prove something is true without really actually giving you even the slightest idea why the thing is true, while barely satisfying the requirement of proving it. The other is that proofs by contradiction are just harder to read. And so if you can prove something by direct proof or by contrapositive, that's better. Now, the way I framed proof by contradiction before was that the goal was to prove some statement R. I want to note what proof by contradiction looks like if the thing we're proving is actually an implication. So, namely, if the statement we're trying to prove by contradiction is the implication P implies Q, well then what's not R? Well, it's P and not Q. And so then our proof outline starts with suppose not R, that is, suppose the implication is false, which is to say it starts with suppose P and not Q. Now, P and not Q might actually look fairly familiar. Namely, P is the thing that you get to suppose in a direct proof, and not Q is the thing you get to suppose in a proof by contrapositive. So often, especially when you're learning proofs, proof by contradiction seems great because instead of only getting to assume P or only getting to assume not Q, you get to assume both. But then there's a question of what your contradiction is going to be. So you do that, you do some math. Now, if you start a proof by contradiction of an implication in this way, there are two particularly dangerous paths that you can go down that I want to highlight for you. One of them is where you do some math and eventually end up at therefore not P. Now, that is indeed a contradiction. Why is it a contradiction? It's a contradiction because P and not P can't both be true. Likewise, you might lead to therefore Q. which is a contradiction because not Q and Q can't both be true. So if those are valid proofs, why did I say these are dangerous paths to go down? Well, let's look at this one first. You start with supposing P and not Q, and you eventually get to Q. What did you really do? Well, you really supposed P and proved Q. That is, what you really did is you took a direct proof and you wrote it in a complicated way. So what's this dangerous path, where you start by assuming P and not Q and get to not P? Well, really, you assumed not Q, and then you got to not P. So this is really a proof by contrapositive. And you really, really, really don't want to write up a direct proof as a proof by contradiction, or a proof by contrapositive as a proof by contradiction, because both of those, again, are much harder to read, much harder to check, much harder for the reader to understand, much harder for you to understand, etc. So be super careful when you're writing up proofs. If you're going to use proof by contradiction, make sure you have not followed one of these outlines where you've just actually used direct proof or actually used proof by contrapositive. Okay, so as promised, I'll now give you the two classic, beautiful proofs. Both of these go back to at least the ancient Greeks, possibly further, but at least to the ancient Greeks. And so the first thing I'm going to prove for you is that the square root of 2 is irrational. And before I go any further, I want you to notice proving any number is irrational is going to be annoying because of the definition of irrational, right? Rational is this beautiful there exists statement about there exists a P and a Q, such that P and Q are integers, and the number is P divided by Q. So then saying a number is not rational is really saying what? This is really saying that for every conceivable pair of integers, P over Q is not the square root of 2. So once you get good at this, you'll sort of be able to recognize, just from the definition, that showing something is irrational is going to be way uglier than showing it's irrational, because showing something's rational is a there exists statement, and so showing it's irrational is a for every statement, and for every statements are worse to prove. So let's look at what this proof actually looks like. So we're going to suppose, for sake of contradiction, that the square root of 2 actually is rational. That is, again, we're supposing the thing we want to prove is false is actually not false, that it's actually true. And so now where do we want to get? Well, I want to get somewhere where I can see that this can't possibly have been right. But getting there, in a proof by contradiction, is always going to be a bit of a journey. So let's go on this journey together. So let's just explore what happens when the square root of 2 is P over Q. Well, then, 2 is the same thing as P squared over Q squared. And so, in fact, what does that mean? That means P squared is equal to 2Q squared. Now, this actually tells me something that I might not see right away. Namely, this tells me that P squared is even. And that's just because if K is Q squared, then P squared is 2K. So it's even by definition. And now I'm obligated to remind you of something we proved a very long time ago. In fact, I believe this thing we proved was our very first example of a proof by contrapositive. So I'm now going to call that thing a lemma, because I'm going to use it as part of my proof here. Namely, if x is an integer and x squared is even, then x is even. And since this proof is so quick, I'm just going to go over it again. Namely, we prove the contrapositive, which is that if x is in Z and x is odd, then x squared is odd. Okay, so we'll suppose x is odd. Well, then there exists a k, such that x is 2k plus 1. So x squared is 4k squared plus 4k plus 1. And so if L is 2k squared plus 2k, then x squared is 2L plus 1, and so x squared is odd. So we can now use this result. As soon as we show that something squared is even, we know the thing itself has to also be even. Hint, by the way, There is one homework question about this proof, and that question asks you to, instead of proving that the square root of 2 is irrational, you need to prove that the square root of 5 is irrational. And the part that's different in that entire proof from what we're doing now is this lemma needs to be replaced with proving that if you have an integer where x squared is a multiple of 5, then x is a multiple of 5. I'll leave proving that to you, but that's the key piece you need for the homework question. But now let's return to our proof that the square root of 2 is irrational. And let's remember the universe we're in now. We're in the universe where the square root of 2 is rational. So we're in a universe that we hope to discover doesn't actually exist. But if square root of 2 is rational, well, then we've shown that there exists a p and q in the positive integers, such that the square root of 2 happens to be p over q. We've rewritten that so that it involves integers. Okay, so we squared both sides, and so now this is an identity, this p squared equals 2q squared. This is an identity of integers instead of real numbers. And I every day prefer to work with integers than real numbers. So that's better. And so we've shown that p squared is even, because we could go ahead and let k be q squared here. But now, since p squared is even, by the lemma we just proved p is even. And what does that mean? That means that there's some letter, let's call it a, such that p is 2 times a. And now I can plug that in to this equation, and that will give me that thus 4a squared equals 2q squared. And in particular, that will give me q squared is equal to 2a squared. And this maybe looks slightly familiar, because this is basically exactly the place we were a second ago. Except now, instead of p and q, I have q and a. But by exactly the same argument, now q squared is even, and so there exists, let's call it b, such that q is equal to 2b. Now, the temptation here is to go put this back into the original equation, and now we've got another equation, and we can keep doing this forever. But I want to make a new observation, which is that if I go to write square root of 2, back where we were originally, that's p over q. But it's also now, because p was 2a and q was 2b, this is now 2a over 2b, which is to say it is a over b. And so not only can square root of 2 be written as p over q, it can also be written as a over b. Now, is that a problem? Well, not really. I can write a third as 2/6, for example. And so there's no uniqueness of the way of writing rational numbers. But if you remember back to Mrs. Johnson's 4th grade class or whatever, you are probably always told that when you write a rational number, you're supposed to write it in lowest terms. Namely, you're supposed to pull all of the common factors out. And if you look closely at what we've just done, what we've actually proven is that in the universe where square root of 2 is rational, it's impossible to write square root of 2 in lowest terms. Because we said, suppose you just write square root of 2 as some fraction, and we proved that fraction is not in lowest terms. And so, if you want to think about it this way, you could apply exactly the same argument to a and b. And so you would generate a c and a d, where this was actually 2c over 2d, so this was really c over d. And then you could do it again and generate an e and an f, and a g and an h, and an I and a j, and so on forever. You could keep writing this in quote-unquote lower and lower terms. Namely, you keep canceling a 2 from the numerator and the denominator, hoping that you'll eventually cancel all of the 2's, but this proof shows you'll never cancel all of the 2's from the numerator and denominator of this fraction. Thus, we've proven that square root of 2 is a rational number that cannot be written in lowest terms. But all rational numbers can be written in lowest terms. So this is a contradiction. And that ends the proof. So if you go back to my original outline of what proof by contradiction looks like, you start by assuming not r, so in this case we assume square root of 2 is rational. And then we got to some statement where the statement was somehow false. And I called that statement Z here. In this proof, this is our statement Z. The fact that square root of 2 is a rational number that can't be written in lowest terms. Because we know we can write every rational number in lowest terms. And so every proof by contradiction that you ever read is going to have this sort of storybook feel where you start and you see at the start that they're going to a contradiction. And then you just have no idea what the contradiction is going to be. In this case, the contradiction is that we found a rational number that can't be written in lowest terms. But the contradiction could be literally any piece of math. It could end up contradicting the fundamental theorem of calculus. Or it could end up contradicting the Taniyama-Shimura-Wiles theorem, which is in fact what the proof by contradiction of Fermat's last theorem ended up doing. There are many possibilities. It should be noted, by the way, that when this theorem was proven, it struck quite a blow to the Greek mathematicians at the time. Because as it happened, the Greek number system was only capable of expressing rational numbers. And so there was a tacit assumption that the Greek mathematicians were making without realizing they were even making it, that all numbers were rational. And so when Hipparchus actually discovered that the square root of 2 is irrational, he wasn't trying to find an irrational number. He was actually trying to figure out how to write square root of 2 as a rational number, because he just took for granted that it was possible to do it. And in the process of writing down the kind of algebra that we wrote down today, he came to realize that it was actually impossible. And so then he went and told his friends about the cool thing he had discovered, and fearing that this would destroy all of mathematics as it was known, they killed him to try and keep it secret. And as you can guess from the fact that I'm now here telling you this story, that didn't end up working. But on to happier stories. Now let's talk about Euclid's proof that there are infinitely many primes. Or at least a proof that we know goes back to Euclid, but we don't actually know if Euclid is the first person to prove this or not. This is really, to me, a pretty striking thing for the Greeks to have even thought about, much less have proven. Like the last thing we proved about the square root of 2 being irrational, the idea of proving that there's infinitely many primes is really slippery. Because if you try and think about what it's really saying, well, there's not finitely many primes. But it's important to realize finite numbers can still be preposterously enormous. So I could, for example, write down 1 trillion primes, and even if I write down 1 trillion primes, I'm only 0% of the way there to proving that there's infinitely many primes. And even if I write down 1 trillion more, I'm still only 0% of the way to proving that there's infinitely many primes. And so proving something like that there's infinitely many of, frankly, anything is a really difficult task. And it's really hard to conceptualize, before you see it, what the proof of this result is going to look like. I would dare to say that because of the magic of this statement that there's infinitely many primes, that this is probably, mathematicians considered collectively, it's probably their favorite theorem. And I say that because people have written down hundreds, if not thousands, of different proofs of this fact. So what I'm going to present for you here is Euclid's proof, but there are tons of other proofs that if you're interested, you can find. Now, this is also going to be by contradiction. So how is this going to start? Well, I'm going to suppose the opposite. So that is, I'm going to suppose that there's only finitely many primes, and I'm going to name all of those primes. So I'm going to go ahead and call those names P1, P2, up to PL. And so just to emphasize this L here in the subscript of the last prime, that's the total number of primes. So if it happens that there's 7 primes, which would be surprising, but if it somehow happened there are 7 primes, then L is 7. If it happens there's 158 primes, then L is 158, because that's just how many things are in this list. The next step is a work of genius. The next step is to do something so non-obvious and so striking that it's just sort of awe-inducing. Namely, the next thing Euclid says is, Well, consider what happens if you multiply all of these primes together and add 1. Why would you do that? But I think it's better to approach this proof rather than from a view of seeing how you're going to come up with your own version of this, where you think of something miraculous out of the blue. Instead, I'd encourage you to think of this proof like you think of art or literature or any of these sorts of things. Appreciate this as a simple act of beauty that this proof works. That the correct step here is in some sense to multiply all the primes together and add 1. And that, as you'll see, once you've thought to do that, everything's just going to sort of fall apart in our hands. Side note, by the way, in the homework, I asked you to prove something slightly different from this. And so you're going to need to come up with your own little miraculous step there. Here's my hint. When you go to find that little miraculous step in the slightly different question I've asked you to do in the homework, do almost exactly this, but instead of putting a +1 here, put a -1 here. That's my hint. Back to Euclid. So what does Euclid do with this number? Well, Euclid knows something about this number. Namely, Euclid knows this number is definitely at least 3, right? I mean, it's way bigger than that, but there's no way this number is possibly 1, right? Because at least there's 1 prime, 2. And so if I multiply 2 by a bunch of other primes and add 1, I'm going to get a number here that's at least 2. So it can be written as a product of primes. This is the fundamental theorem of arithmetic, and by striking coincidence, it happens to be the part of the fundamental theorem of arithmetic that I proved for you in the previous video. So since n can be written as a product of primes, I'm just going to pick one, and I'm going to call it q. And so, since q is a prime factor of n, that means q divides n, and so that means that n can be written as k times q. And so what is this saying? This is saying that in terms of the division algorithm, n is in the k times q plus 0 bucket. Why is that important? Well, it's important because it tells us, as you'll see in a second, that this prime q that I've found, it can't be one of my p1 through pl. Namely, I'm claiming that if this q actually is one of our universe of primes, and in the universe we're living in now, q has to be one of those primes. Why? Because we assumed we have a list of all the primes in the universe. And so if we have a list of all the primes in the universe, and q is a prime, then it has to be one of the primes that's in our list of all the primes in the universe. And in that case, that q is one of those, then I'm going to say that n's actually kq plus 1. Why is that? Well, it's actually written that way up here. Namely, n here is just this product that includes q plus 1. This hat, by the way, you'll see people use this hat when they want to do things like this. All it means is I'm writing down the product, but I'm omitting the term pi, because pi was q, so I just pulled the q here. And so instead of writing the q that was equal to pi in this part of the product, I wrote it at the end, just to make evident that if I let this be k, then n is kq plus 1. But this is our contradiction. Because on the one hand, we have proven that n is in the kq bucket. But on the other hand, we have proven that n is in the kq plus 1 bucket. And so what have we actually contradicted? We've actually contradicted the uniqueness of buckets from the division algorithm. Or if you want to say it in fancy terms that don't use the word bucket, it contradicts the uniqueness of the remainder in the division algorithm. But since we have our contradiction, that means we have completed our proof. And we know now that there's infinitely many primes. Just take a step back and appreciate what happened. Euclid started with the statement there's infinitely many primes, and wanted to prove it. And in order to write down the proof, he had to invent this number, this fictional number, because remember, the universe that this number exists in doesn't exist, because this is the fake universe where there's only finitely many primes. And not only did he have to invent this number out of nowhere, he then had to identify that this invented number contradicts the division algorithm. And note, no part of this theorem says anything about the division algorithm. And so in order to come up with this proof, you have to put together all of these pieces that you don't necessarily have any reason to think ought to be put together. And that's what makes this proof beautiful. Now, this really goes to the overall message I want you to take away about proof by contradiction. Proofs by contradiction are often the most beautiful and exciting to read. And so, us mathematicians, when we're teaching you these classes, we're often most excited to show you the proofs that are the most exciting to read. And so if you sit in a typical math lecture, not this one, but if you sit in a typical math class, probably half or 3/4 of the proofs you see a professor present will be by contradiction, because those are the cool ones. But when you then go to the homework in said classes, it is almost never going to happen that you're going to be expected to produce a proof by contradiction. Because no one is going to expect quite this level of creativity out of you in a typical homework set. And so as a result, it's very common that if you're used to seeing proofs by contradiction all the time in lecture, that you'll attempt to emulate that and use it a lot. The reality is, as I said before, you're not going to need proof by contradiction very often. When you do, you'll feel like a god, and it will be glorious. But most of the time, you'll be able to get by with direct proof and proof by contrapositive, as we've talked about before. So that's why I've sort of saved this part until last, because this is really preparing you less for the doing of proofs and more for the artistic appreciation of proofs, both in the latter half of this class, but especially in future classes you might take. Last up, I promised to show you a couple of just weird proofs that don't really follow any of the models of what we've done so far. The proofs I'm going to show you all fall into the category of existence proofs. That is, all of these proofs are going to be things that prove a there exists statement, but they're all going to prove that there exists statement without actually giving an example. These are what are so-called non-constructive proofs. Now, every time we've gone to prove an existence statement, we've just done it by saying, oh, hey, here's an example, 127, 8, 92, whatever it happened to be. But sometimes mathematicians are able to prove something exists without actually being able to write it down. And a lot of the results that you get out of this way are especially bizarre. And so you might have heard, for example, the Banach-Tarski theorem, which says that if you start with a solid sphere, it's possible to break up the solid sphere into pieces and put it back together in such a way that the two pieces assemble to two spheres of the same size. Which is every bit as nuts as it sounds when I describe it that way. Definitely, this was originally proven using one of these existence methods. That is to say, it was proven in a way where you couldn't actually figure out what that way is to sort of slice up the sphere in order to put it back together into two spheres of the same size. Just in case you don't believe that that says what I actually say it says, I'll spell this out, so if you want to look up the Wikipedia page for the Banach-Tarski theorem, there is the spelling. So I'll do two examples of existence proofs. One to convince you that this idea isn't actually that crazy, and then one to show you how it actually works, and then I'll hint at one last one that we'll talk about later. So here's the statement. There's some digit, by which I just mean one of those 0 through 9 things that shows up on a number pad, that occurs infinitely often in the decimal expansion for pi. And so, really, all you have to do to convince yourself that this is true is to think about what the universe is like where this is false. Namely, in that universe, each of the 10 digits show up finitely many times in pi, in which case, how many digits does pi have? Well, the sum of 10 finite numbers. And even if those 10 finite numbers are huge, that would still only total up to a finite number of digits. But pi, like every real number, has infinitely many digits. even the decimal number 1 has infinitely many digits. It just so happens that after the decimal point, all of those digits are 0. So, in fact, not only pi, every real number has the property that some digit, 0 through 9, occurs infinitely often in the decimal expansion. For 1, that digit is 0, and that's the only digit with that property. But what I'm getting at here is, for pi, we know there is such a digit. There can't not be. However, no one can give an example of such a digit. No digit is known, at least of the time I wrote these notes, that it shows up infinitely often in the decimal expansion for pi. Now, if you were to ask any mathematician who studies this sort of thing to guess, they would probably guess that all the digits 0 through 9 show up infinitely often in the decimal expansion for pi. But who knows? And so sometimes like this, you can actually see by sort of the quantity of something that exists, so for example, the fact that there's infinitely many digits, that something has to happen even without being able to identify when it happens. So we've thought about the closure of rational numbers under something like addition. If I add 2 rational numbers, I get a rational number. If I multiply 2 rational numbers, I get a rational number. The irrational numbers, by and large, don't work that way. If I add 2 irrational numbers, I might well get a rational number. You can think of an example, or if you multiply 2 irrational numbers, you might get a rational number. You can think of an example of that too. But when it comes to powers, things can get kind of ugly, because it's hard to think about what happens to rational or irrational numbers under powers. And so, it might be very easy to convince yourself that, hey, maybe it's true that if you take an irrational number to an irrational power, then you get a rational number. That's possible. But it turns out not to be true. It turns out there definitively exist irrational numbers with the property that if you raise the first irrational number to the second irrational number power, you get a rational number. And I can prove that for you in the following bizarre way. Now, first of all, I'm going to notice that because I'm doing this example now, it has to involve the square root of 2, almost, because the square root of 2 is the only number we've been able to prove is irrational. I mentioned this before, but proving pi is irrational is way harder than something we can do in this class. It's true, pi and e are both irrational, but it turns out to be really difficult to prove. But we do happen to know that the square root of 2 is irrational, because we proved it earlier this video. So I'm going to start by looking at x being the square root of 2, and y being the square root of 2 to the square root of 2 power. So to start with, I'm going to note that maybe y is rational. This is a completely content-free sentence, by the way. Maybe anything. It either is rational or it isn't, but I have no idea if it's rational or not. It's not exactly like you can type it in a calculator and see if the digits repeat, because maybe the digits do repeat, but not until you get to the 7,000th digit or something. So for a long time, no one knew if this number was rational or not. But I want to point out that if this number y does happen to be rational, well, then we've proven this, because I can take a and b both to be square root of 2. But probably if you were forced to guess, you would guess probably this number is irrational. And it turns out I can cover you there too. Namely, if y happens to be irrational, then it's a valid choice for a. And so then I claim you can take a to be y and b to be x. Okay, and so you probably are scratching your head here, unless you're already doing the algebra. But what happens is if you do that, then a to the b is the square root of 2 to the square root of 2 to the square root of 2, which happens to be the square root of 2 to the square root of 2 times the square root of 2, which, and then you can see where this is going. This is the square root of 2 squared, and that's 2. Definitely rational. And so again, here we're talking about what happens if y is irrational. If y is irrational, then, well, it's a valid choice for a. Square root of 2 I know is irrational, so it's a valid choice for b, but then that gives you an example of an irrational number to an irrational power that is rational. And now, the key thing here is that we don't need to know whether y is rational or irrational in order for this proof to work. This proof has 2 pieces, one of which exists in a world that doesn't exist. Like, one of these worlds is completely fake. And we don't need to know which one to know that this is a valid proof. This actually isn't so uncommon in terms of proofs. So there are a lot of big unsolved problems in math. So the biggest unsolved problem now is called the Riemann hypothesis. And you'll see quite often that papers will get published where they'll say, okay, our theorem is true if the Riemann hypothesis is true. But then even weirder than that, you'll see papers that say our theorem is true and our proof depends on whether the Riemann hypothesis is true or not. But then they'll actually give two different proofs in the paper, one proof if the Riemann hypothesis is true, and one proof if the Riemann hypothesis is false. And so what that's saying, if they do that, is that in the future, once we know the Riemann hypothesis is true, they can throw out the 20 pages of the paper that talk about what happens in the world where the Riemann hypothesis is false, because that world never existed. Likewise, if someone were to tell you that the square root of 2 to the square root of 2 was irrational, then you could throw out the part of this proof where we talked about what happened if it was rational. And so this is, again, getting into the whole weird part of math where we can know something exists without being able to write it down. So, last up, I want to note that the square root of 2 is not sort of as irrational as it's possible to be. And the way I'm going to say that is that this is related to rational numbers by algebraic operations. And all I mean by that is that if you take x to be square root of 2, then if you take x and multiply it by itself, multiplication being an algebraic operation, then you get 2, and this is rational. Likewise, if you took something like the cube root of 5, this similarly is related to the rational numbers by algebraic operations, because y times y times y is 5. And even numbers like if you take the square root of 2 plus the cube root of 5, it's a little trickier to figure out how exactly to connect this, but it's not so hard to see that this is in some sense something that if I multiplied it by itself, I'd get 2, and something if I multiplied it by itself 3 times, I'd get 5. It's not so hard to believe you could get back to the rationals with this. So I'm not going to call this a definition because I'm being very informal in describing this, but numbers like these are called algebraic. So all algebraic really means is that it's possible to sort of connect it in some fashion using algebraic operations back to the rational numbers. And so these are sort of the irrational numbers that aren't so bad, basically. And then the alternative is what we call transcendental numbers. And as the name transcendental sort of implies, these numbers carry a great degree of mystery with them. In some sense, a number that's transcendental is totally unrelated to our usual number system. So people in the 1800s were starting to think about this and starting to understand what the structure of the algebraic numbers looked like. And it was not at all clear at the time whether any transcendental numbers existed. There are lots of algebraic numbers, but there is this big question mark about transcendental numbers. Now, there were a lot of suspicions, and you probably have some suspicions too. So you might, for example, suspect that pi and e are transcendental. It would happen, you're right. Mathematicians at the time mostly suspected that as well. But no one could prove it, and there was maybe this lingering hope that maybe it turns out that actually pi is something like the square root of 2 plus the square root of 3 plus the square root of 7 or something. Maybe there's a really nice simple formula for pi that just no one has found yet. But, of course, no one knew. Now, the natural end to this story would be to say, okay, and then so-and-so proved that pi is transcendental, and thus they settled the question that transcendental numbers exist. That's not what happened. In fact, this question was settled by a Jewish mathematician by the name of Georg Cantor. What Cantor was interested in, and a topic that we're going to talk about after the break, is the question of how big infinite sets are. And so there's sort of this idea that, well, maybe all infinite sets are the same size. Like all sets of size 7 are the same in some sense. Maybe all infinite sets are just size infinity, and it's that simple. But what Cantor actually figured out is that that's not true, that actually there's some infinite sets that are more infinite than other infinite sets. And more to the point, what Cantor showed is that if you take the set of just algebraic numbers, and you look at its size, and you compare that to the size of just the set of all real numbers, it turns out these sets aren't the same size. The algebraic numbers are a subset of the real numbers, but they're a proper subset. And so what Cantor proved is that in fact the set of algebraic numbers is strictly smaller than the set of all real numbers. And so in fact one consequence of this, and we'll talk about this again when we talk about this later, so this is really a plug for later in the course, but one consequence of this is that this really means that 100% of real numbers are transcendental. In a very precise sense, but of course not all of them are. And so this is the same sort of thing if you've come across in a probability class, for example, the fact that it's possible for an event to have probability 1, but yet still sometimes fail to happen. In the same sense, 100% of the real numbers are transcendental, but there are plenty of numbers that aren't. So one interpretation of Cantor's result is that if you picked a real number at random, with probability 100%, it would be an example of a transcendental number. Of course, you'd have to do it really random. You couldn't just ask someone on the street, because if you did, they'd probably tell you 4. And 4, it turns out, is related to the rational numbers, so it's algebraic. And so for this period in time, mathematicians knew that there were transcendental numbers, and knew not only that there were transcendental numbers, but in fact, almost every single number had to be transcendental. But even despite infuriatingly knowing that, no one could prove that any single number happened to have this property, until Louisville did it much later. It should be noted, this is still an area where there's all kinds of things people don't know. So even in the state of current knowledge, people know, say, pi and e are transcendental. But in fact, no one knows if pi plus e is transcendental. In other words, there's a basic fact about our two most fundamental mathematical constants that even with many millennia of mathematical study, all of humanity does not know how to answer. And I at least find that really captivating. But that's all for this week. On Monday, there'll be the test, then there'll be break, and then hopefully after 2 weeks of sitting at home, you'll be ready to come back refreshed. I hope everyone has an absolutely wonderful break, and I promise I'll see you next time.